Good afternoon, Professor Alvarado. My name is Jaime Andres Rosario and my colleague Wilfredo Acevedo. We're presenting the greenhouse project Phase C2. First, we have the outline. The topics that we're going to be discussing during these presentations are the following: system integration, plan manufacturing and integration, plans and procedures, system operation plan like user manual, performance estimate, project planning, and the system budget. For the system integration plan, we have the 3D view of the house. Here we have like I said, the 3D view of the house. The red flag are the photovoltaic system, and for yellow we have the HVAC VRF system. Here we can see the condensing unit, the solar panels, the inverter, the connection between the grid with the Puerto Rico energy system, and the battery from the photovoltaic system. Here in the top view we have the assembly of the different evaporator according to the size and cooling capacity of each area. Here we have the evaporator from the working station, the entrance, conference room, and the two rooms that the office has for storage or other purpose.
Good night, Professor. My name is Wilfredo Acevedo. I'm the owner of the photovoltaic system. And in this part, we have the system integration plan, where we have the known and the unknown data. Where in the first known data, we have the area of the office, that is 988 square feet. The hours of sun peak in Atoray, Puerto Rico, that 5.6 hours. The initial charge load of the office, that was a 55 thousand watts hours day. The outside temperature, that is 92 grades Fahrenheit. The comfort temperature as 7225. The heat transfer by the sun in Puerto Rico, that is 5.53 kilowatts square meter, and the existing primary line of grid in the house. And the unknown data, we have the analysis of 21 photovoltaic panels, the cooling load, the calculate CPM, the total power provided of the PV panels, and the inclination of the all PV panels, and the inside temperature without HVAC. Where we have in this part, we have the trajectory, the sun at the house. In the right picture, we have the cooling load, that is the old evaporator producing the cooling of the house. And we have the outside temperature, the area available to assemble the condenser and the photovoltaic system. And in the left image, we have the all system integrated in the house, where we have the battery, the solar, the hybrid inverter, and the existing power grid. In this part, I'm going to talk about with the manufacturing and integration solar system. In this part, we have the assembly of the all equipments of the solar system, that is the 410 watts photovoltaic cells, and the transfer switch for non-critical loads. And we have the hybrid inverter and the Fortress lithium battery. In this part, we have the drawing of the photovoltaic panel, that is a Eagle photovoltaic panel. The specification, that is a monocrystalline panel, that we established this device in Phase B, where we have the all dimensions of the photovoltaic panel. In this part, we have the hybrid inverter 8 kilowatts of the power potential. That this is the immediate energy that require the house, and this is all the the dimensions of the hybrid inverter and the requirements that needs to establish the operate in the house. In this part, we have the lithium battery of 10.24 kilowatts. We have the lithium battery configuration that is established in phase B in the plating weighting method, and we have the all dimensions of the battery in this drawing. On this part, we have the manufacturing integration of the solar system, where we have the general vision. That is in the first step. We have the place and fix the photovoltaic cells and locate the battery and the hybrid inverter. Then in the first point, we have to place the photovoltaic panels between 16 to 18 degrees of inclination. Place the lithium battery and the hybrid inverter at the wall. Uh, Double threaded screw with APDM gasket for fixing the photovoltaic panels on paved roof. Double threaded screw with external hexagonal M10 per 300 millimeters for wooden substructure with the threaded nuts. Sealing gasket and bracket with eyelets. And in the second step, we have the string array. Uh, we have established the 7 PV panels in series and 3 PV panels in parallel with a maximum voltage of 300 47.2 voltage. We have in the right part, we have the place and fix the PV panels with respective monocrystalline panel, lithium battery, hybrid inverter, and the screws. In the second step, and in the right part, we have the strings array, 7 panels in series and 3 panels in parallel. And the third step, we have the wiring correction, that we have established the connection of the system according to the design. In the and 2.2, we have established the first connection from two PV panels to the combiner box using a 14 AWG THHN in Cooper cable with 25 amperes capacity. In the 2.3, use a AWD THN in Cooper number 6 wire of 75 ampacity from the combiner box to the hybrid inverter. Finally, we have the use AWG THN in Cooper to the hybrid inverter for non-critical loads. That we have the a little in picture of the wiring connections, and the other two picture what is the cables that the connection needed. And finally, we have the pipes distribution that we have to conduit from PV panels array to combiner box using a scale 14 of middle inches, and we have the conduit combiner box to the scale 40, and finally we have the conduit from the inverter to non-critical panel for a sub-panel scale, and in the left image we have the pipes, and finally we have the results that we have the components that is the PV panels, the hybrid inverter, lithium battery, and the finished part we have the all the assemblies of the photovoltaic system.
Okay, here we have for manufacturing and integration of the house. Here we have the two ANSYS drawings. showing where going to be placed the condensing unit and where going to be placed the evaporator according to the calculations. The condensing unit will be a 5 tons VRF that we will be connected with 5 evaporator unit inside the house according to the cooling load capacity of each area and the task that is going to be performed in each area. Here we can see that in the working station we have the bigger evaporator because it's the bigger area. Here we have a 21,000 BTU evaporator. In the entrance we have 9,000 evaporator. In the conference room we got the 9,000 evaporator. In the room 1 we have 12,000 evaporator, and the other room another 12,000 evaporator. All of those evaporators will be connected to this one condensing unit of 5 tons. Here we can see some drawings from the manufacturer. In this case, is GRI. These drawings are we look for them in internet because the manufacturer doesn't give it to the public, so we can see how the condensing unit will look. You can see that we'll have two fans for removing the heat from inside the house. Inside there will be the compressor. Here are the communication cables port, and here are the refrigerant lines port. Here's a side view and a back view of the behind view of the on the 5-ton condensing unit. Here we have the evaporator units. Each evaporator will be the same, but there's maybe inches bigger or smaller depending on the cooling capacity of the evaporator. Here we can see the bottom view. This is the base. This part will be placed in the wall with screws, and this is a side view of the evaporator, how it will look. The evaporator will receive the heat here and remove it from here, the airflow. Here we have the instructions or some manual for the technician how the system will be installed. First, we need to place the condensing unit in the roof and place some plastic boots and an anchor system to prevent the condensing unit to fall when there's a windy day or a storm. After placing the condensing unit in the roof, we can go inside the house and place the evaporators in the marked locations that I showed before. We need to use 3/8 Tapcon to place evaporator bases to the wall. After we perform that step, we can go to step 2 that will be performing some holes to penetrate the refrigerant line cables. To perform those holes, we need a shipping hammer like this, a big shipping hammer because it's a concrete 8 inches concrete wall, and we're going to use this cup to penetrate the wall in 3 per 3 inches hole. That's going to be depending where it's necessary or not, because some walls you don't need to penetrate, but for connecting to the condensing unit or maybe to another evaporator you need to penetrate. After that, you can place the refrigerant lines across the entire office, connecting it with branches to connect evaporator with each evaporator. And in each evaporator, you need to place some bulb valves. Bulb valves will help to prevent some to turn off the entire system when there is a malfunction. Bulb valve, you place it in each evaporator, and if you have a malfunction in the evaporator, you can close the bulb valve and solve the problem without turning off shutting down the entire system. After placing the refrigerant lines for gas and liquid lines, you need to place the communication cables. These communication cables will be from the condensing unit to the first evaporator, and then will be like this, like a cycle. Like this condensing unit will supply this evaporator will communicate. It will be a series connection. After all the series is done, y regrese otra vez a la condensadora. After that task is complete, you can now go to the final step, that is the weldment of the lines. You need acetylene and oxygen to weld the copper lines, and because of high pressure refrigerant, you need silver to make that weld. After the weld is done, the system is ready to flush and to make the vacuum for operation. Here we have how it will going to look. These are the condensing unit, the equipment that we're going to use. We're going to use the GRI VRF, and we'll be using 5 of these evaporators.
Continuing to the operate system, we have the grid sellback. This mode allows solar arc to sell back any excess power produced by the solar panels grid, and the options that is main menus, system settings, grid setup, limiter, grid cells. And we have the sensors, limited sensors, battery temperature sensor, PV shutdown, and CAN bus. Another slide of operate system, we have the programming battery settings. Select the battery size, main menu, system settings, battery setup, bat and battery capacity. We have finally the battery type. Navigate to the charge menu and set the value appropriate to your battery chemistry. And the main menu, system settings, battery setup, and the charge. And finally, the battery discharge percentage. Finally, we have the limiter sensor automatic setup. Install the limiter sensors, battery, and grid connection also required before starting auto setup. Navigate to the advanced tab of the basic setup screen. Touch on the gear icon, select and press OK. Wait for the solar arc to finish its learning and verify sensors correctly configured. In this part, we have the troubleshooting. We have the LCD is not powering on. Check all connections. Um, Panels are not producing. Check the also solar panels connection. Turn on the PV disconnect. Check that the PV volt input voltage is not greater than 500 voltage. And the step 3, panels are not producing much power. We have the PV wire strip length. Try settings system to grid cells. In the first step, we have the system not keeping batteries. We have to check the charge setting in the charge menu. System is beeping. Check the system alarms menu to see which alarm has been tried. Most alarms will self-reset. And finally, we have in the sixth step, we have the system connects to grid and quickly disconnect with the verify your neutral wire is connected. Check your frequency. Finally, overloading verify the grid input and the load output wires are not swept. In this part, we have the maintenance of the system, carry out tests to the inverter control through the management software or directly on the control screen to guarantee efficient operation. Check control cables, electrical connections, remote monitoring system switches. Check the battery status, verify the system load counter after the system has been isolated from the grid. The state of charge on the battery are in an optimal situation of the measured voltage is no less than the nominal voltage. Component cleaning, visual inspection to detect any deterioration, system voltage control. To control the efficiency for photovoltaic system, it's recommended to follow the following scheme. That is, make the reading of the meter, measures the production of the electricity for a period of least a month, and mark the data report. In this way, the daily energy production we also recorded. Um, the daily production varies depending on the gradation, on the solar graph gradation. For the reason to obtain more precise value, it is advisable to take a reading for 1 year.
For system operation plan or user manual in the HVAC system, after installation is complete, you must perform a flush using solvent to remove all the dust and impurities that the well creates. After that, you can close you can open you can close the lines and make a vacuum until you reach 800 microns at least, but it's supposed to be lower than 800. We usually use like 500 or 400. In this case, this is a visual representation of how that process will look. This is the micrometer and this is the manifold gauges that will let you know if there is some leakage or the lines are open or if there is a great vacuum and all that stuff. This micrometer is more precise because it's a digital apparatus that will help also to be more precise. After the vacuum is done, you can open the refrigerant valves and you can start the startup process of the machine. Here we have the condensing unit main board. In this board you can see some buttons. Usually the manufacturer manuals tells you what button you need to press, and after for making the startup. In the startup you must know that all evaporators must be turned off. Then only you will turn on the condensing unit here, pressing the start button for 5 seconds. After the condensing unit start blinking, she is making the startup test. She is communicating with each evaporator, assigning the evaporator job and communicating with each evaporator. After the blink stop, the condensing unit will automatically shut down, or maybe you need to shut it down. After that process is done, you can now go to the to the controller or to the panel and turn off the equipment and turn on the equipment, and you can start running your equipment. And for your personal use, you only just just need to go to the controller and place the power button on and off. That's it. You don't need to do anything more. Recommendations: you need for better efficiency of the system, you need to place the set point at 75 degrees Fahrenheit, or you can place it at 70. It will be working at the best efficiency. Why? Because when we perform the cooling load capacity, we shows a zero point 0.5 tons por encima of our calculations, because to have redundant in case there's too much heat one day, or in case we want to ahorrar más energía, we want more energy saving. Another recommendations is give the maintenance like one or three or every 3 months, depending on the use and the people that are coming inside and outside the office. For the maintenance, you need to open the evaporator unit like this. It will look like this. You need to spray the solvent, let it rest like 30 seconds to 1 minute to the solvent dilute all the dust. After that, you can go with a hoe or with a pump machine and you can spray off the solvent and the dust, and it will look like this part. This is the dirty side and this is the clean side. Also, the turbine needs to be cleaned. After that, you can go check the refrigerant pressure lines to see the pressures if everything is good, and check the voltage, because voltage fluctuation can give an error to the system. In case you need to troubleshoot, you need to know that you need to sometimes capacitor contactors can give problem. For capacitors, you can use a multimeter and place it in continuity to check the continuity of the capacitor. For the contactor, you can check the voltage or the amperes, and communication cables also you can do the same process. From just refrigerant pressures, if you seem to have low pressure, you can use a manifold gauge and to detect if there is some leak or if there is some refrigerant that you need to add to the equipment. Another thing, you need to check the junction box ampere, because sometimes those cables can get rust or there is many problems and you may need to change it or connect it better. Also, if the equipment is giving you an error code, you can access the PDF documents that the manufacturer gave to you to detect what is the main problem. In case you don't have that error code, you can make all the troubleshooting process that I mentioned before. For performance estimators, the system MOPs, we have various MOPs from the different phases. From phase B, we state that the system should use photovoltaic panels. Our performance was that the system will use 21 monocrystalline photovoltaic panels. We need also to reduce the cost of energy, and the initial cost of energy was $295, and now the owner only needs to pay $5 with 36 cents. For the HVAC system, must be 4 to 6 ton unit HVAC system, and when we make our load calculation, we conclude that we can run our system with a 5 tons HVAC system. That's from phase C1. The required flow must be lower than 9,880 cubic feet a minute, and when making the calculations, we obtain 3,794 cubic feet meter. For the budget, we can't exceed the $43,000, and our ultimate budget was $32,927. For the system should produce 7,838 kilos, and our performance was 8,008 kilowatts was the performance. And finally, the equipment must be 50 years, and our equipment is going to have 50 years of life.
And this is the system budget. Um, in this table we have the new system budget that is divided of the two subsystems of HVAC and the solar system. We have the equipment, materials, labor, and the total cost was 32,927.19 dollars, and versus the initial budget that is $43,000 and 97, and we have the on the range of the budget of the established in phase A. And finally, we have the project plan for phase D and phase F. Thanks for your attention, Professor Alvarado.